Well, again, I want to review just a little bit about some of the things that we did actually before break, and that's to relook at this electromagnetic force. So you've seen this before, I think, but let's re-emphasize it here. As I said probably a couple of weeks ago, the electromotive force, EMF as it's called in lots of places, is horribly misnamed. It's not electrical in nature. It's not a force. Doesn't have the units of force, and maybe I guess motion is motive is okay, but anyway, not very well named. A lot of times these are called DC power supplies, and it's which is essentially any device that maintains a constant potential difference across its two ends, called its terminals. And these are used to produce direct current, which is currents that flow in only one direction. Let's take a look at the situation. Here I've got a typical, maybe a C cell battery or maybe a AAA cell. Has a button end and a flat end. It's marked to positive and negative on the cell as well. And outside the battery, the current naturally flows from the high potential, the positive charge here, flows in current down to this point. And uh, if that's all it did, the action of the battery, then ultimately I would get more and more positive charge here, neutralizing more and more of the negative, and it would the current would rapidly die out. But instead, uh, uh, the action of a power supply is to take that positive charge current and maintain the current flowing in this direction. Now, inside, current naturally likes to flow from high to low potential, high potential to low potential around the circuit, external to a battery, but inside there's something in there that makes the current, the positive charge, move in a direction it doesn't want to move. If I got a chunk of positive charge here, uh, for me to move it from this point, take positive charge and move it over to here, takes work. I have to apply a force to it, which I've indicated, because this positive charge is attracted to that negative and it's repelled by this positive charge that's at this terminal. The electric field is this direction, and the way a positive charge wants to move, there's an electric force that's the charge, Q, times the electric field, so it would be in the opposite direction. So I have to provide some other force, not electrical, to move this charge in a direction it really doesn't want to go from an electrical standpoint, namely from negative to the positive internal to the cell. Well, that leads us to the definition of the EMF of the power supply, or the EMF of the battery in this case. Usually represented in script E. Sometimes people will use capital V or little v for it, but we're already using V for potential and potential difference, and sometimes even volts. So I'm going to use the script E for the, the EMF of a cell in this case. And by definition, what that is the non-electrical work done on a positive charge delta Q inside the cell to move it from the negative over to the positive. So it's this extra force that I have to apply to push it in a direction that it doesn't want to go. So that's what's on top. And I like to represent that as delta W, the work, the amount of work non-electrical that's done. It's going to be done by this force F, wherever that force comes from. Per unit charge. So I move a charge delta, positive charge delta Q from here to here inside the cell. That's the top. And I divide that by the amount of charge delta Q that I moved. And that's the definition. If you look at the units of EMF are the units of work done by divided by the units of charge. And we know the units of charge are the coulomb, and the unit of work. Well, work is force times distance, and Newton meter, and a Newton meter is a joule. So the units of work are the same as energy. And so we don't have a a specific, uh, although it's defined in a different way, we see a common expression, joule per coulomb, and we'll just use the same name that we gave that as volts. It turns out it's exactly the same as what we'd previously defined to be the unit of potential, namely volt. Now, in that expression, this delta W is really the non-electrical force. The work done is force dotted into displacement as you move that positive charge from the negative terminal to the positive terminal. This positive charge from the negative over to the positive as part of that current flow. I think we gave this gravitational analogy. Let's look at that. So here I've got the charge, in this case a mass, that gravity pulls down and bounces around. So this is like the resistor, and then it rolls around over here, and then there wouldn't be any flow around it at all if we stopped here, because there's a gravitational force, mass times gravity, on this mass m, and some external thing to continue this flowing around. I have to apply a force F. Here there's a person presumably picking it up and lifting it up and putting it over here. So this force F has to be enough to overcome the gravitational force. And that part is like the EMF. For a typical cell, I'm sure you've seen this in the laboratory. I believe you've done this experiment by now. But I've got a cell, D cell maybe, the positive end, the negative end, and the current that flows through it. Here's the external resistor, sometimes called the load resistor. But the current has to flow continually around in this fashion, and so the current has to also flow through the cell itself, or the battery. Okay? And we represent this really as a model that there's gunk and stuff inside here, chemicals, there's paper and things. So this current has to flow through it, and so the battery presents a resistance to the current that it itself produces. Okay? And so generally we model a real battery or a real cell with an ideal battery, which is this here, the EMF, and an internal resistance of the cell, which is given there. So we could replace this by an ideal cell and internal resistance. The two terminals of A and B give us the voltage difference across from the negative to the positive side of this difference here. And we can compute that pretty easily. If there's a current I flowing through it, then the total voltage drop as I go from B to A, well, I'll get an increase of potential due to the EMF of the cell, but I'll lose some due to the internal resistance of the battery, so I subtract off minus IR. And then that's internal to the cell. That gives me the potential difference from B to A. That's really delta VA, is E minus IR. Usually you just represent that as V. I call that the terminal voltage. It's the voltage that if you hooked up a voltmeter across A and B, across these two leads here from the positive to the negative, that's the voltage you would measure. Okay? Again, R is the internal resistance, a characteristic of the battery, and the EMF, it's also a characteristic of the battery. For a D cell, they're 1.5 volts, and so the EMF is 1.5 volts. The internal resistance for a D cell is maybe a tenth of an ohm to sometimes half an ohm, but relatively small. I is the current that flows around in the circuit, and it's the current produced by the cell. This plot should look familiar to you from one of the labs. You can make a plot of the voltage, terminal voltage versus the current. When I is 0, it's at the EMF, and if you look at this, if I'm plotting it versus I, then the slope is really minus the internal resistance. When the voltage is zero, then one gets the maximum current here, and you get a straight line plot for this equation as shown. The maximum current that a battery can produce is the EMF divided by its internal resistance. Now, generally, this is just some terminology, but we generally need more voltage than a single cell can produce. And so what one does is you put several cells together in series. And these, I'm thinking of as ideal cells. And so flat end, positive end, flat end, positive end, flat end, positive end. Each one of them will give me an E, an increase in voltage as I go from one point to the other. And so the total voltage increase from this end, from the left end, all the way to the right end is 3 times E. E plus E plus E in this particular case. And this really is what's meant by a battery. A battery is a series of things in series. Could be a battery of tanks, a battery of capacitors, or in this case, a battery of cells. You know? So technically, cell is one item, and a battery is a series connection of several of them. Lots of books will do this instead of writing them out like this. That takes a lot of space, and they will sort of cram all these together and move them together and put this. And so a lot of times you'll see this symbol used for a cell or a battery. Yeah. The I'll probably just reduce it to just this, and you know, how you produce that 3E is something that you can do by putting together the cells that you have to produce the total voltage that you need across the cell. Notice the polarity of these is really easy to establish too, because the long bar and the rest of the symbol is always the positive. It's the positive charge, it'd be the button side of these. And the short bar is always the flat side or the negative end. So this is the low potential side, the high potential side, the positively charged terminal, and the negatively charged terminal.